Hi, I'm Shalina George, your trainer for this course. I am excited to guide you through your AI testing journey. In today's rapidly evolving technology landscape, mastering AI testing can significantly boost your career. Are you ready to embrace the future and become ISTQB certified in AI testing? This comprehensive course closely follows the official ISTQB syllabus, ensuring you are fully prepared. You'll explore everything from machine learning fundamentals, data handling, neural networks, testing complex AI based systems, to leveraging AI itself for smarter testing. I am confident that you will successfully complete the ISTQB AI testing certification using these carefully structured lessons that include real world examples, interactive chapter wise quizzes, practical exercises, a realistic mock exam, and tips on enhancing your profile post certification. So, why wait? Develop the essential skills, boost your confidence, and ensure your success in the ISTQB AI testing certification exam. Let's take your testing career to the next level. Let's begin your journey in AI testing now. A little bit about me. I have nearly 20 years of experience in quality assurance and testing, and I work as a senior QA manager at a leading multinational company. I also hold a master's degree in computer science and several ISTQB certifications like Advanced Test Manager, Agile Technical Tester, AI Testing, Foundation Level, and much more. I've led and mentored QA teams and delivered high quality results on big, fast paced projects. I'm excited to bring all that experience here and guide you through the world of AI testing in this course. Now, let's take a look at the ISTQB roadmap. As you can see, AI testing is a specialist certification, and the prerequisite for the certification is the ISTQB foundation level. About the course outline, the course is organized into 11 chapters covering everything we need for the AI testing certification. We'll start with an introduction to AI and then discuss quality characteristics for AI based systems. We'll dive into machine learning basics, including handling ML data and evaluating ML performance metrics. We'll explore neural networks and how to test them, then move into testing AI based systems and specifically AI specific quality attributes. We'll also learn about methods and techniques for testing AI systems and what test environments are needed for AI based software. Finally, we'll cover how AI itself can be used for testing. This roadmap shows the journey we'll take through the course content step by step. In this course, the learning objectives are categorized by ISTQB's cognitive levels K1 through K4. K1, remember, means you should be able to recognize and recall key terms and concepts. K2, understand, means explaining ideas in your own words, comparing and classifying concepts, and giving examples. K3, apply, is about knowing how to use a concept or technique correctly in a given scenario. And K4, analyze, goes deeper, breaking down a problem or procedure into parts to understand it fully. These levels show how deeply you are expected to grasp each topic. In practice, this ranges from simple recall of facts all the way to applying concepts and analyzing complex situations. Mastering these will not only prepare you for the exam but also enable you to handle real world testing challenges more effectively. We have a variety of course materials to help you learn and practice. There's the official syllabus, which covers all the key AI testing concepts and methodologies you need to know. You'll have comprehensive lecture videos like this one to walk you through the topics, along with well structured presentation slides for easy review. We have also included exercise questions and solutions so you can practice and check your understanding as you go. There are sample quiz questions and a sample exam with answer keys and explanations to give you a feel for the real exam. And finally, a glossary of software testing terms is provided as a handy reference. All these resources are there to support you and make your learning experience as smooth as possible. Let's go over the basics of the ISTQB AI testing certification exam. The exam consists of 40 multiple choice questions that you will need to complete in 60 minutes. It's a closed book exam and will be invigilated. If English isn't your native language, you're typically allowed an extra 15 minutes. To take this exam, you must have the ISTQB foundation level certification first. That's a prerequisite. The questions are weighted by those K levels we discussed. You will see around 4 K1 questions worth 1 point each, 29 K2 questions 1 point each, 3 K3 questions 2 points each, and 4 K4 questions 2 points each. That's a total of 47 points. To pass the exam, you need to score at least 31 points. So make sure to grasp each level of learning objective, as the exam will test a mix of recall, understanding, application, and analysis skills. Welcome to Chapter 1, where we introduce the fundamentals of artificial intelligence. In this chapter, we'll define what AI really means and discuss how our understanding of AI has evolved. We'll look at different categories of AI systems and compare AI based systems to traditional software. By the end of this chapter, you will have a solid foundation in core AI concepts that will be important throughout the rest of the course. Let's dive in. First, what do we mean by artificial intelligence? Generally, AI is the capability of a man made system to acquire knowledge and skills and then apply them to solve problems or perform tasks. In other words, an AI system can learn from experience or data and use that learning in new situations. Now, you might have heard of the AI effect. This term describes how the definition of AI tends to shift over time as technology advances. When a once impressive AI achievement becomes common, people stop thinking of it as AI. For example, a few decades ago, a computer beating a human at chess seemed like true science fiction. Then IBM's Deep Blue actually defeated a world chess champion, which was considered a huge AI milestone at that time. Today, we have AI systems and neural networks that routinely excel at games and tasks once thought to require human intelligence. As these achievements become normal, we raise the bar of what we call AI. So, the AI effect reminds us that what we consider AI today may just become ordinary software tomorrow as our expectations evolve. AI systems generally fall into three categories: narrow AI, general AI, and super AI. Narrow AI, also called weak AI, is designed to perform specific tasks within a limited context. These are the AIs we interact with every day. Think of spam filters that detect unwanted emails, voice assistants like Siri, or Netflix's recommendation engine. They are very good at the one thing they are programmed for, but they don't really understand beyond their specific task. General AI, sometimes called strong AI, refers to a system with broad, human like cognitive abilities. In other words, it could reason, learn, and understand any intellectual task that a human can. Right now, general AI is mostly theoretical. We haven't achieved a true general AI yet. Super AI goes even beyond human intelligence. This would be an AI that not only matches human reasoning but also leverages immense processing power and knowledge far exceeding any humans. It's the kind of AI that could improve itself rapidly and potentially do things no human could. The point where an AI transitions from general intelligence to something vastly superior is often referred to as the technological singularity. Now, let's compare AI based systems to conventional software systems. A traditional or conventional system is usually rule based and deterministic. That means it follows a set of predefined instructions or rules, and given the same input, it will always produce the same output. For example, a calculator app, it's a conventional system. It's programmed with the rules of arithmetic. If you give it two numbers to add, it will follow a fixed procedure to return the sum every time. In contrast, an AI based system is typically pattern based and adaptive. Instead of just following rules set by a programmer, it can learn from data and adjust its behavior. Think of an image classifier or a movie recommendation engine. These systems improve as they see more examples. They don't have one fixed rule for every situation. They figure out patterns, like what a cat looks like or what kind of movies you enjoy, and adapt their predictions accordingly. The key difference is that AI systems can learn and evolve from new data, whereas conventional systems will always do exactly what we originally programmed them to do, no more and no less. Bias in AI systems is a crucial quality concern, especially these days. In simple terms, bias refers to systematic errors in the AI's outputs that favor one group or outcome unfairly over others. Another way to put it is think of an ideal AI system that's perfectly fair. Bias is how far off our system's results are from that ideal fairness. We have seen very real cases of inappropriate bias in AI. For instance, some bank loan recommendation systems turned out to be biased, offering less favorable terms or outright rejections to certain minority groups, even when their financial profiles were similar to others. There have been recruitment AI tools that unintentionally favored male resumes over female ones because they learned from past hiring data that itself was biased. Even in the criminal justice system, risk assessment algorithms have been called out for bias against people of color. Bias can creep in through many channels. Sometimes it's the people who design the system. Their unconscious biases reflect in the rules or data they choose, and often it's in the training data. An expert system which follows predefined rules might inherit the biases of the expert who wrote those rules. A machine learning model might reflect biases present in its training dataset. These biases can relate to various attributes: gender, race, ethnicity, sexual orientation, income level, age, and so on. An AI might not explicitly use those attributes, but it could use proxies like zip code or education level that correlate with them, leading to biased outcomes. When we test AI systems, we have to actively look for these biases. It's not enough for the system to be accurate overall. We need to see how it performs across different groups or scenarios to ensure it's not consistently skewed. In short, unfair bias is a quality defect in an AI system, and addressing it is part of our job as testers and developers of AI. Welcome to Chapter 5, where we explore machine learning functional performance metrics. In this chapter, we learn how to evaluate the effectiveness of a machine learning model's predictions. We'll cover the confusion metrics and key metrics like accuracy, precision, recall, and the F1 score, as well as when to use each of it. By the end, you will understand how to choose the right metric for different scenarios and be aware of additional evaluation measures and industry benchmarks. The actual output of many binary classification algorithms is a prediction score. The score indicates the system's certainty that the given observation belongs to the positive class. To make the decision about whether the observation should be classified as positive or negative, as a consumer of this score, you will interpret the score by picking a classification threshold and compare the score against it. Any observations with scores higher than the threshold are then predicted as the positive class, and scores lower than the threshold are predicted as the negative class. Confusion metrics. To evaluate model predictions, we start with the confusion metrics for binary classification. This metric summarizes prediction versus actual outcomes in four categories: true positives, false negatives, and true negatives. Think of a binary classifier. Example, dog versus not a dog. A true positive is a correct prediction of the positive class. That's when the model says dog and it is indeed a dog. A true negative is a correct prediction of the negative class. That is when the model says not a dog and that's correct. A false positive is when the model predicts positive, that it is a dog, but the actual is negative, that it's not a dog. It was a false alarm. Conversely, a false negative is when the model predicts negative, meaning it says it's not a dog, but the actual was positive. In this case, it missed a dog. This 2 by 2 table of outcomes forms the confusion matrix and is the basis for many performance metrics. Let's cement this with an example. Imagine a dog classifier tested on 1000 images. The results form the confusion matrix. TP equal 900, FP equal 40, FN equal 10, and TN equal 50. Here, it's a dog is the positive class and not a dog is the negative class. So out of 910 actual dog images, which is 900 plus 10, the model correctly identified 900 and missed 10. Out of 90 actual not dog images, which is 40 plus 50, it correctly flagged 50 as not dog, but mistakenly labeled 40 of them as dogs. Laying this out, the matrix's rows might be actual labels, dog versus not dog, and columns predicted labels, dog versus not dog. The 900 in the dog cell is true positives. 50 in the not dog is true negatives. 40 in dog, not dog cell are false positives. And 10 in not dog, dog are false negatives. This example will help us compute various metrics. Let us look at accuracy. Accuracy is one of the simplest metrics. It measures the overall correctness of model. Formally, accuracy equal number of correct predictions divided by total predictions. In terms of our confusion metrics, that's TP plus TN divided by TP plus FP plus FN plus TN. We often express it as a percentage. Accuracy tells us what fraction of all predictions of the model got right. It's a quick gauge of performance. An accuracy of 90% means 9 out of 10 predictions are correct. However, as we will see, accuracy alone can be misleading if the data is imbalanced. For instance, if one class heavily dominates the dataset. So first, let's calculate it for our dog classification example. Using the dog classifies confusion matrix, accuracy equal TP plus TN divided by the total. That is 900 plus 50 divided by 900 plus 50 plus 40 plus 10. This equals 950 divided by 1000 equal 0.95, which is 95% accuracy. This means the model correctly identified 95% of the images. In our example, the high accuracy reflects that the classifier is generally performing well. However, note that accuracy treats all errors equally. It doesn't tell us if the mistakes were mostly false alarms or misdetections. We will need other metrics to get a full picture of performance. Alright, now let's apply AI to some real testing activities. First up, handling bug reports. This is often called defect triage or defect analysis. Basically, sorting through reported defects to prioritize them and find duplicates. AI can be of a huge help here. Imagine you have hundreds of defect tickets coming in. AI can read those reports and do useful categorization. For example, using natural language processing, an AI tool can analyze the text of defect descriptions and determine what functionality or component is impacted. It picks out keywords or topics from the bug report and uses those to tag the defect. Maybe it figures out, this bug is more about the login module, or this is a performance issue. This automatic categorization helps group similar issues. The AI can highlight when multiple reports are likely describing the same underlying bug, flagging duplicates so we don't waste time on redundant reports. In fact, AI-based categorization is super useful in large projects. Like imagine the Windows or Firefox teams getting thousands of reports and AI can sift through those. AI can also assess defect criticality, Machine learning models trained on past defect data can learn which kinds of defects tend to cause critical failures or affect a lot of users. So, when a new bug report comes in, the AI might predict how severe or critical it is likely to be. This helps the team prioritize fixing the most impactful bugs first. And what about assigning the bug to the right person? AI can assist with defect assignment too. By learning from history which developers fixed which types of bugs in the past, an AI model could suggest this new bug about the payment module should go to Alice because she's resolved similar issues before. This smart assignment can save time in triage meetings and get the bug to the best owner faster. So, in summary, for defect analysis, AI acts like a smart triage assistant. It categorizes new reports, finds duplicates, highlights critical issues, and even recommends who should fix them. All of this speeds up the defect handling process, allowing testers and developers to focus on actually resolving the problems rather than sorting them.